Welcome to Andrew's Key Lectures. Topic is line defects, area defects in crystals, Burgess vector, plastic deformation. Teacher Anand Mohandas. The arrangement of atom in all materials contain imperfections which have profound effect on the behavior of the materials. Lattice defects can be sorted into three: point defects, line defect, surface defect. Let us look into line defect and surface defect. Now, line defects are two types: screw dislocation, edge dislocation. The edge dislocation occurs when an extra half plane is inserted, and screw dislocation results when displacing planes related to each other due to shear stress. So, why defects are important? There are a lot of properties that are controlled or affected by defects. For example, electrical and thermal conductivity in metals are controlled by or are affected by defects. Electronic conductivity, diffusion, and we know diffusion controlled by vacancies, ionic conductivity controlled by vacancies, plastic deformation in crystalline materials controlled by dislocation, which is line effect, and colors can be affected by defects, mechanical strength also affected by defect. Let us see surface defect. Surface defect is also called planar defect or area defect. Now, there are two types of surface defects, three types we are mentioning: grain boundaries, twin boundaries, stacking fault. Now, grain boundaries you can take. Grain boundaries, two different places or between different crystals. It may arise at the boundary between two grains or small crystals within a larger crystal. The rows of atom in two different grains may differ in directions, leading to a mismatch across the grain boundary. Next is twin boundaries. A twin boundary has different crystal orientation on its two sides. And stacking fault is considered as a planar defect and is called stacking defect because this defect is created due to fault in the stacking sequence of the atomic planes in crystal. And for twin boundaries, unlike a grain boundary, the orientations are not random but related in a specific mirror image way. So, let us look into Burgess vector. Magnitude and direction of the lattice distortion resulting from a dislocation in a crystal lattice is Burgess vector. In edge dislocation, Burgess vector is perpendicular to the dislocation line, and in screw dislocation, Burgess vector is parallel to the dislocation line. Now, how to measure Burgess vector? Step 1 is a circuit is made around the dislocation line in a clockwise direction, with each step of the circuit connecting lattice sides that are fully coordinated. Step 2 is this circuit, which is Burgess circuit, is then transferred to a perfect lattice of the same type. And step 3, because of the absence of a dislocation within this circuit, it fails to close on itself, and the vector linking the end of the circuit to the starting point is the Burgess vector. You can see QM is the Burgess vector here. So, the first circuit we drawn is transferred to a perfect lattice circuit of the same type, and the difference is the Burgess vector. Now let us look into plastic deformation. Plastic deformation is a permanent alteration of shape, form or texture of a material due to action of stress. In metal, there are two types of mechanism of plastic deformation. One is slip, another one is twinning. Slip is very important. And slip, it involves the sliding of blocks of crystal over one another along different crystallographic planes, which we call slip planes. And the slip is a line defect. Twinning is a form of deformation caused by shear stress. The plane of atoms forms into two mirror image planes along a boundary called the twin plane. And twinning is a surface defect. So, the two main mechanisms of plastic deformation is slip and twinning. And I hope you have understood plastic deformation. Thank you for watching the video. Thank you.